Hello everyone, my name is Büşra Tansaatçı and I am PhD student at Fırat University. Today I will be presenting our study titled Deep Learning Based Classification of Cutting Tool Wear in Dry Turning of Titanium Alloy Using Thermography. This research was conducted under the supervision of Mustafa Ulaş and Turan Gürgenç, along with the valuable contribution of Engin Ünal. Importance of tool wear detection. Meshing efficiency critical for optimizing efficiency and ensuring surface integrity, particularly in difficult-to-cut materials like titanium. Condition-based maintenance facilitates the transition from scheduled tool chains to condition-based maintenance in high-value machining. Industry 4.0 offers a scalable solution for predictive maintenance and zero-defect production in aerospace and automotive sectors. Introduction. Titanium challenges. Despite high strength and corrosion resistance, titanium's low thermal conductivity leads to extreme temperatures and cutting zone. Monitoring needs. Real-time and non-contact monitoring is essential for accurate tool change intervals. Research contribution. This study introduces a non-contact monitoring framework that utilizes infrared thermography to capture distinctive thermal signatures associated with cutting tool wear in titanium alloy turning. By leveraging transfer learning architectures like Inception V3 and GoogleNet, the proposed approach achieves up to 99.79% accuracy in classifying wear stages, providing a robust and computationally efficient solution for real-time Industry 4.0 applications. Experimental setup and data equations. Material. Titanium alloy was used. Meshing parameters, dry cutting and 45 mm minute cutting speed and 0.1 mm RPM feed rate. Thermal monitoring, real-time visualization and tracking of thermal distribution within the cutting zone. Dataset approximately 56,000 thermal images labeled according to ISO flank wear standards. Methodology Deep Learning Framework. Models comparative evaluation of three transfer learning architectures GoogleNet, VGG16 and Inception V3. Optimization stochastic gradient descent algorithm with a cross entropy loss function. Image cropped to a fixed ROI resized to 1056 pixels and constraints enhanced to 1.5. Figure B data process pipeline for thermal image based tool wear classification. Video capture, frame extraction, ROI crop, resize, contrast enhancement, labeling low, medium, high, tray test split 80 and 20, model training, evaluation. Results classification performance. Model accuracy Inception V3 achieved the highest classification accuracy among the evaluated models, reaching a success rate of 99.79. VGG 16 99.60, GoogleNet 99.53. Efficiency: GoogleNet provided a 70% reduction in training time, 9 hours, compared to Inception v3 Figure 2. Training time per epoch for GoogleNet VGG 16 and Inception v3 models. Results details metrics. All models performed well on an independent test dataset consisted of 12,101 images. Inception v3 exhibited the highest macro average F1 score, 0.9974, confirming its superior generalization capability across all wear levels. While Inception v3 leads in accuracy, GoogleNet provides a highly competitive class accuracy of 99.93% for high wear detection with significantly lower computational cost. Misclassification were primarily confined to transition boundaries between medium and adjacent wear classes, where thermal patterns are visually similar. Results details metrics. All models performed well on an independent test dataset consists of images. Inception v3 exhibited the highest macro averaged F score, confirming its superior generalization capability across all wear levels. While Inception v3 leads in accuracy, GoogleNet provides a highly competitive class accuracy of 99.93% for high wear detection with significantly lower computational cost. High wear detection with significantly lower computational cost. Misclassification were primarily confined to transition boundaries between medium and adjacent wear classes, where thermal patterns are visually similar. The most important class, the high labeled class, has the following value as shown in the table. Discussion. Software-driven intelligence. The framework demonstrates that deep learning models efficiently substitute manual feature engineering by learning distinctive thermal signatures directly from RGB heat maps. Real-time decision making. GoogleNet's 70% reduction in training time confirms that high accuracy tool monitoring can be deployed on resource constrained embedded at a competing device within CNC systems. Unlike standard steel-focused models, this system is optimized for titanium alloys, where intense heat accumulation at the tooltip serves as a reliable predictive indicator for zero-defect production. Scalable maintenance. The Automate framework enables a seamless transition to condition-based maintenance, reducing unscheduled mission downtime and material waste in high-value aerospace and automotive manufacturing. Predictive thresholds identified thermal patterns at where transition boundaries provide critical software logic for triggering tool chains before catastrophic failure occurs. Conclusion and future work. Thermography combined with deep learning is a robust foundation for automated toolware monitoring in high-volume titanium machining. The proposed approach can support Industry 4.0 smart manufacturing, zero-defect production. Industrial Choice GoalNet is most suitable candidate for embedded edge computing in CNC system due to its efficiency. Future directions, validation under wet MQL, cutting conditions, and expanding the dataset to include diverse tool geometries. Thank you for your attention. If you have any question, please contact.